Okay, so for today's deep dive, we are going way, way down in temperature, pretty much to absolute zero.
But we're not just talking about the temperature itself.
No, not at all.
It-
We're talking about the result. Bose-Einstein condensation, BEC, the fifth state of matter.
and it is. I mean, the physics is just mind-bending.
It really is. It was predicted by Einstein almost a century ago, this idea that atoms could stop behaving like tiny little billiard balls and
And just act like a single giant coherent wave.
Yeah.
For decades, BEC was, physics white whale.
So every atom surrenders itself, and they all start acting as one big group. Is that the quantum soup we hear about?
That's it, exactly. What's happening on a technical level is that their de Broglie wavelength, you can think of that as the atom's quantum fuzziness, it gets so large it starts to overlap with its neighbors.
And that overlap forces them all into the same quantum state.
Right. It's a purely quantum statistical phase transition. And poof, the gas becomes a single macroscopic wave packet.
So we'd had breakthroughs like superconductivity way back in 1911 and superfluidity in 38. Why did BEC stay so elusive for so long?
Well, the biggest problem was that atoms don't want to stay as a gas when they get that cold.
They just clump together.
They condense into a liquid or a
Yeah.
solid, in the normal way, long before you can reach that critical quantum temperature. So they had to figure out how to do it at these incredibly low densities.
100,000th the density of air, something like that.
Yeah, and that required a whole new approach, a multi-stage process.
Okay, so if conventional cooling just turns your atoms into, a tiny ice cube, how did they get around that?
Stage one was laser cooling.
Which sounds completely backwards, using light to make something colder.
It does, but think of it less like a heat ray and more like
Right.
using photons to carry away kinetic energy. You tune the lasers just right, and they slow the atoms down, pre-cooling them.
Okay, so laser cooling gets you close, but not all the way.
Not even close. It just sets the stage. For the final push, you need what's called forced evaporative cooling.
Right, this is like cooling a cup of coffee by blowing the steam off the top.
Precisely. You trap the atoms magnetically, and then you let the hottest, most energetic atoms literally escape the trap.
And the ones left behind get colder and colder.
They rethermalize at a much, much lower temperature.
And the MIT team, with Wolfgang Ketterle, they hit a really specific wall here, didn't they? Something about Majorana flops.
Yeah, that was a huge problem.
Yeah.
In the very center of their magnetic trap, the field was basically zero,
The weakest point in the chain.
the weakest point. And in that spot, atoms could lose their spin orientation, and the trap just couldn't hold them anymore. They'd just fall right out.
So they were leaking the very atoms they needed to keep the density high. How did they plug the leak?
Well, they literally used a plug, an optical plug. They aimed this focused, repulsive laser beam right into that zero field center.
A sort of quantum force field.
Exactly. It just pushed the atoms away from that danger zone, kept the density high, and allowed the evaporative cooling to finally work.
And on September 29th, 1995, it did. They had it, definitive proof.
They did. And once they cracked that toad, BECs became this incredible lab for exploring quantum mechanics on a huge scale.
Like the atom laser in 1997.
Right. But the real showstopper was in 1999, with a direct observation of atom amplification.
You're saying they could amplify a matter wave, just like you amplify light in a regular laser?
That's it. They'd send in a small matter wave. It would pass through the BEC, the active medium, and it would come out amplified by a factor of 10, even 100.
Wow. And they also proved its coherence, right, by making two of them interfere.
Yes, in 97. Two expanding condensates created these beautiful interference patterns, which was just stunning proof that the whole thing was behaving as a single coherent wave.
For me, though, the most spectacular image is the vortices, seeing quantum mechanics in motion.
Oh, absolutely. The Abrikosov lattices in 2001. By spinning the condensate, they created over 100 tiny, perfect quantum whirlpools inside the gas.
You're literally seeing quantum mechanics with your own eyes on a scale you can observe.
It's just incredible. A complex quantum phenomenon made visible.
The speed of all this development was just astonishing. And now BEC is this robust, almost easy-to-use tool for quantum physics. So what does this all mean now?
It means we have this unique, highly controllable quantum fluid that lets us study fundamental physics in a way we just never could before.
So the foundation is set, but it feels like the story is still just getting started.
Completely. And here's a final thought for you to chew on. We've seen these amazing vortices, but what about sound? We're not talking about normal sound waves, but second sound, a purely quantum wave of heat that can travel through these superfluids.
So the next question is, can we make these quantum soups sing?
Exactly. Exploring that and developing practical high-power atom lasers. That's where this whole field is heading, and it promises to get even weirder.